If there are no questions about this, I can move on to the next paper. This was also an assignment for you to watch. Any questions about this? So the method that you have in the previous paper was a little bit expensive to come up with adversarial examples, because for each example, for each image, to come up with the perturbation, you had to solve an optimization problem, which is going to take a while to be solved. This is a cheap way of generating adversarial examples. As soon as you see an image, you're going to add the gradient of your loss, the sign of the gradient of your loss with respect to your input to the image, and that's going to perturb it. And why is this useful? Because now you can do data augmentation. You can perturb your data, that's going to give you new data, and you can use that to train your architecture. And this could be a way of defending against adversarial examples. So you're going to see this pattern. Somebody comes up with an idea to attack a neural network, and then another person is going to come up with an idea to defend against that attack and make your neural networks more and more robust. Any questions about this? So the question is, how do we get the exact perturbation that causes the network to fail? So you have two methods up until now. Up until this slide, we covered two methods to come up with a perturbation that's gonna cause your network to fail. One of them is this. You have your image, you have the corresponding loss, you take the gradient of your loss with respect to the input, you take its sign, multiply it by epsilon. Epsilon is the magnitude of your perturbation. In this case, it is 0.007. You add these two together, and that's going to give you a new image. That's going to get classified totally different from what it is supposed to be classified as. That's one. The other one was the one from the previous paper, which is you're actually solving an optimization problem. You have your image, you add a little bit of perturbation to it, and then you're going to try to minimize that perturbation because you don't want your perturbations to be too obvious to human eyes. You want to minimize that perturbation subject to your classifier classifying that image incorrectly as another label. Does that answer your question? And one of them is more expensive than the other one. And it turns out that keeping adding these perturbations or these perturbed images to your training data is equivalent to putting a norm, a penalty on the derivative of your loss function with respect to your input. And in the case of a logistic regression, it's going to end up being the L1 norm of your parameters. So you don't want your parameters to become too big, and at the same time, you want to make them sparse. There is a question, how do we decide the optimal epsilon? That depends. Are you the attacker? Are you the adversary? Or are you the one who wants to defend against adversaries? If you are the person who wants to defend, you're gonna have a range of epsilons and add them to your training data. Maybe epsilon from 0 up until a large magnitude, you're gonna keep adding them to your data. If you are the adversary, for this case, as soon as your neural network makes the mistake on an image that you like, then that's game over. But then you're gonna do this, you're gonna look at the success rate, how many times your attack was successful. And that could be a metric that can help you set epsilon, the magnitude of the attack. So there's a trade-off here. If epsilon is too big, the one who is trying to defend against it might be able to notice that there is something different about this image. So there is a trade-off. It shouldn't be too big, it shouldn't be too small. Any other questions? And there is a difference between the attack from the previous paper, which was targeted attack, which means that I give you a label, and then I want your image to be wrongly classified at the label that I specified for you. That's targeted. In the case of red light being classified as a green light, this one is untargeted. It means that you want your neural network to classify a red light as either a green or a yellow, and you don't care which one. So was that clear? Okay, perfect.